Bismillahirrahmanirrahim. Welcome to the 11th lecture on applied statistics course. हमने last time क्या किया था? फिर था उससे पहले याद है क्या करे थे? Continuous distributions. Yeah. So we were looking at cases of continuous distributions. What's the whole idea? In the second module, we studied how to collect probabilities in functions. We call them distribution functions. What were they? PDF, CDF, joint PDF, conditional PDF, yeah? But there we were just talking about generic formulations. In this part, we came back to those and we said, okay, what shape do these fx, small fx take, right? And in that we looked at the discrete case, discrete random variable case, which was where we did discrete uniform distribution, binomial, right? Then there was negative binomial, geometric, and then we looked at Poisson distribution with the law of rare events. Yes. Now, along with those, we went on to look at instances or common cases of fx for continuous case. And there we looked at three. Three distributions. Firstly, the very basic continuous uniform distribution. Yes. Secondly, exponential distribution. And thirdly, we looked at the Gaussian or the normal distribution. And just as in Poisson we had looked at the law of rare events, here we looked at a very special theorem that makes the Gaussian distribution very powerful, which was the central limit theorem. Yeah, so you can revise that, view the videos again, we discussed that in detail. Here I will continue with the Gaussian distribution. We had covered it. What we need to do is just cover one special case of it now, and then we will move on to the fourth module of this course. Yeah. So let's complete our discussion on the Gaussian. We have already recapped on what we did before this. So, क्या shape थी Gaussian distribution? याद है किसी को? Normal distribution. What shape does it have? Bell curve. Very popular bell curve. Even in news you see the bell curve discussed. So it is basically the bell shape or the bell curve. And last time we saw how it develops, often develops as an accumulative or average effect of various underlying random effects. Yeah, so we saw that in detail. I highly advise you to review that lecture, review the video again, read the topic, central limit theorem, because that is the basic foundation of the normal distribution and why it is so powerful. Now, we wrote the formulation for the normal distribution. We said, okay, it has fx and it is a function of two parameters, mean and sigma square, right? So what was it a function of? It's like 1 over square root 2 pi sigma e minus 1 over 2 sigma square x minus mu square. And we had already looked at different instances of what the mean parameter mu does and what sigma does. What was it? Mu kya karta hai? Mean. Yes. What does it do to the bell-shaped curve? So let's say you have this bell-shaped curve. Yeah. If I increase, now this is a mu here, some mean. If I increase the mean, what happens to the curve? Moves to the right or left if you decrease it. If I increase or decrease the variance, what happens? The spread changes. Yes. So that is of course the concept of mean and variance. We have already covered that in great detail in the third module of the course. So now the last thing I wanted to cover for this, it should have been last week, but since we ran out of time, I will cover it now, and then we move on to our fourth module for the course. So now, of course, any distribution that follows this formulation is Gaussian. Yes, that means there can be many of this. Is a family. Yes, this is Gaussian. Then another one with a different mean but same variance, that is also Gaussian. Another one with different mean and different variance is also Gaussian, as long as it follows this formula. So there are several, or let's say this is entirely a family of distributions. Yes. Now among these, one stands out, and it is very useful for comparison purposes. Okay, and that is the standard normal distribution. Okay, it's nothing special. It is the normal distribution, but we say that a random variable that has a normal distribution is standard normal if two conditions are satisfied. The mean is 0 and the variance is 1. Okay, so a very special case of this family is, so this whole family is normal distribution, yeah, and if you have this, this is this whole family of normal distributions. Within this one, there is this special single case. Actually, I should just draw a dot anyway. So it's mu equals 1, sigma square is mu equals 0, sigma square equals 1. Then we say that distribution is standard normal. Okay, and you will hear this a lot in probability theory, and you will see today, even in the 4th module, you will see we will come back to this time. Yeah. So let's establish what it really does. So what does it do to the formula, by the way? क्या हो जाएगा standard normal के लिए? Can somebody help me write it? So let's write it here. We have the green there. It's 1 over square root 2 pi e. So sorry, 2 pi and sigma is 1 now. Yes, standard normal के लिए. Mean is 0, so you have minus 1 over 2 x square, right? So it simplifies to this formula, or it's a special case. Standard normal, any normally distributed random variable whose mean is 0 and variance is 1. Okay, so how would the curve look? Well, the standard normal curve would always look the same, where whatever that is, it will have, let's say, if I can draw here, if this is 0, then it will be peaking at 0, and the variance, the spread, will be 1. Okay, you know how to calculate the variance, so you know, of course, this goes on asymptotically to infinity, but this is what it is the bell curve with mean 0 variance. I'm emphasizing that because after that I will stop saying that. As soon as I say standard normal, you will have to assume that mean is 0 and variance is 1. Okay. Now what's the benefit of doing this? Why do we standardize things? Standard नाम रखा है इसका. Why do we standardize things? क्यों करते हैं? Any idea? वैसे real life में 4 में से GPA सब यूनिवर्सिटीज देती हैं, right? Why do we standardize it? Comparison becomes easier, right? So here also what happens is this. Let's look at the standard normal case. So if you remember, we had, let's say there is a random variable distributed as a Gaussian, let's say, distribution. Okay, let's say this is small x. What is the probability x is less than x? We have a name for that function. What's that called? Probability of this interval x less or equal to x is PDF is different. Yeah, this is the CDF, right? Cumulative distribution function. Yes, f(x). What does it say? The probability x is less than x is here, this area, right? Okay. Now in, let's say, not long ago. Now we have Python, we have computing, we have mobile at our hand. You can find for any, you can give, let's say there is a random variable x that is normally distributed. Often we draw it like this. In your text, I think you draw it as a small n, that's also fine, with a mean mu and variance sigma square, let's say. We have a normally distributed random variable. Yeah. Now, these days, if you know the mean and you know the variance, this has to be capital X. If you know the mean and you know the variance, then you can find this function for any value of small x, 1.5, minus 1.5, 10, whatever you want to find out. Yeah, it's very much possible to do that. But before this, it hasn't been that easy. So you had to refer to tables. Yeah, and in your book there are tables also. Now the problem with tables is, so in the table, what you would write is a particular value of x and what is the value of fx for normal distribution. Yeah. So you would, what would you do? You would put x as, let's say, minus 1.5, calculate this, then do minus 1.49, calculate the area. Each of those you fill here. Yeah. For different x, what would be the fx? Yeah. Now what's the problem? The problem is that these values are different for different mean and variance, aren't they? So if there is another distribution that has a different mean, that variance is for the same x, the area would be very different. So how many tables do you think you will need to write? These days it's very easy, we just code it, we have the codes, calculator, everything, yeah, it does that. But if you really look at it, it's a very hard thing. You will have to make an infinite number of tables if you were relying on tables. But do we do that? Did people do that before Python, before your laptop, mobile had easy access to calculations? No. Humans have been mostly smart, otherwise we would be stuck with huge books of tables. Yeah. So what did they do? They standardized. They said, okay, let's do this. Let's talk about the standard normal random variable. Yeah. So let's say you have this, a standard normal random variable with mean 0 and variance 1. Said, okay, let's write all the table for this guy only. So this is the standard normal table. Yeah. So pick one value of x, minus 2.7, whatever. Yeah. Find the area, write that here. Yeah. Pick another value with some nice up to third decimal place or something. Yeah. Pick another value, calculate the area, maybe here, calculate the area, like those here. Okay. Now for standard normal you need one table. Yes. But what will happen now? Let's say. Firstly, to keep in mind, we use this notation, which is a Gaussian random variable whose mean is 0 and variance is 1. We usually write it as a z. Okay, z is the notation for standard normal distributed random variables. Now, for this variable alone, we create the table. Okay. Now, what about another random variable which is Gaussian distributed but does not have 0 mean and variance? Maybe it has mean mu and sigma square. This might be 10 and this might be 1.5. Can you use this table? No, not directly. But there is a trick they used. We can still use it. We don't really need it much now, but it's good to understand, because that trick we will also use in the 4th module for other distributions, or some other related distributions. Now that trick is this. How do I find the f of small x for a Gaussian distributed random variable which is not standard? using that table. It turns out if you have a random variable, any Gaussian random variable like this, if you subtract its mean from it, you know what happens to the mean of the overall random variable? So this x has a mean mu, yes? Subtract the mean. So what is the total mean? 0? Because it's ex minus e mu. E mu is mu, mean of a constant is a constant. So it's 0, yes? And you divide it by its variance, standard deviation, which is square root of the variance. If you define it like this, then it turns out that any Gaussian random variable, if you remove its mean, divide by standard deviation, it becomes standard normal. So you can prove it. How? Let's see. What is the mean of z now? You already told me, yeah? This is just a divider. So this will be ex minus e mu divided by sigma, or e sigma if you want. Overall, this thing will be 0. Now similarly, you can easily check that the variance of this new random variable is x minus mu divided by sigma, which we are calling now z, for good reason, because we know that actually this random variable has a mean. The new mean, which I will call mu z because I am naming it z, is 0, and sigma z square is 1. So by doing this modification, you have converted this thing into a standard normal distribution. Now back to the question, how can we use this standard normal formula for this guy? Okay, let's look at that then. Let's say I want to find f of small x1 for a Gaussian distributed random variable which is not in its standard form, has some mu and variance, and I want to find fx1. Okay, I go back to definition. What is fx1? Probability x is less than x1. Agreed? That's just CDF defined. Now the trick I can play, I cannot use that table because that table is for standard cases. I can do this. I can say, okay, I will x minus mu. Can I do that? Yeah. What should I do on the right then? Same thing. So the probability x is less than x1 is the same as x minus mu is less than x1 minus mu. Yes? Now, standard deviation is a positive number. You know that, yes? So variance is always squared, so positive number we use. So you divide it by a positive number, the direction won't change, and it will still be like that. So the two probabilities are exactly the same, isn't it? But notice, by doing that, you converted this left hand side into z, which is standard normal. Now this left hand side is a random variable which is standard normal. Its mean is 0, its variance is 1. So now you can calculate this probability. How? You are saying probability, let's call this guy z1, and as I said, they were written for standard normal, so I should have written z here. They are for standard normal. We'll call this z1. Now how do you find this probability? Very simple. Find z1 here. If this value turns out to be 0.5, then find 0.5 here, read fz, and that is your answer. Yes, because that fz1 will be the same as fx1, with the understanding that z1 is defined how? Whatever you had x1 minus the mean of this guy divided by its own standard deviation. Yeah. So with one table you can find the CDFs, yes, of any Gaussian distributed random variable. Okay, so that is the power of the standard normal distribution. and we will use it again in the next module. Okay, any questions? समझ आ गया, idea हो रहा है? Yeah. So just redo it on paper. It's not hard to follow and it's very convenient. There's nothing much to spend time on this guy. Anyway. So let's take a solid example. For instance, let's say you have a Gaussian distributed. I use this symbol for distribution. Okay, how it is distributed. So x in Gaussian or normal distributed with mean and sigma square, where its mean is 3 and sigma square is 0.25. Okay, now is x standard normal? Firstly, no. Yes, because standard normal requires mean 0, variance 1. It's a very simple thing, but I'm repeating it so just to hammer it in forward. Yeah, but later on we just assume that you know it. Okay. So now if I want you to find probability x is less than 2.3. Yes, and all you have are those probability tables for the standard normal distribution. Now they are there in your book, appendix A3. Please make sure that you know how to read that table. Okay, it's not just 2 columns, it has multiple columns because they want to use third decimal place of z. Just see how to read it. It's not a rocket science. It's very easy. Anyway, so now you can't read this. If you directly read from here, you will find okay, where is 2.3, and I will, because this is your small x. Yes. So if you read off 2.3 from here and take the value, you are wrong. Why? This was never written for non-standard norm. It was written for standard norm. So go back to what we discussed. You say, okay, the probability of this guy is the same as saying x minus the mean 3 divided by the standard deviation, square root of that 0.5 less than 2.3 minus 3 divided by 0.5. Now, as we have already proven, this guy is now standard normal. So this is z and this is small z. So calculate this. I've already done that. It turns out to be 1.4. So you're saying I want to find probability z less than minus 1.4. This equals this equals this. Yes. Now you are in the standard normal format. Now go to the table, find minus 1.4. Whatever value you see, that is your answer. So you should see actually 0.080. Smart, huh? So any mu or sigma, all are covered by one table. Okay. Let's look at another example. Let's say there is a normally distributed and a variable, some mean and variance. The mean is 40 and the variance is 4. Okay, and we want to find probability x is greater than 43. Yeah. How do we find it now? Yeah. So firstly, you do as you did before. You say, okay, this is probability x minus 40 divided by 2 greater than 43 minus 40 divided by 2, the standard deviation. Yes, and that is probability. Now this thing is standard normal. It is z greater than 1.5. But now you have a problem. What's the problem? This is standard normal. Yes? The table is not written for greater. CDF is less than. Yeah? So what do you do? 1 minus. Yes? So very logical thing to do is either this is the probability is either this value is greater than 1.5 or less. This is mathematical reality. Yes? And in continuous cases, the actual 1.5 doesn't matter. Its probability is 0. So you can do as 1 minus probability z less than 1.5. Those of you who did not understand this, simply know this: when probability z is greater than 1.5 plus probability z is less than 1.5 equals 1. Equal probability z equals, if you want, you can have that z less or equal, doesn't matter, because for continuous case, probability at any single given point is anyway 0. Yeah, we discussed that. So now you can use the table, find 1.5, find fz, put that here, and you have 1 minus that. That is your answer. Yeah. So this was to bring home the idea of Gaussian distribution. Okay. Now we go to our, this is done. This was actually part of the previous lecture. The next one will also use it, so it's good that we covered it today. We will actually see this showing up for other distributions. At the start of the course, I said how many modules in this course? 5. Yes? क्या क्या थे? पहले 3 तो याद रहे. Yes, assigning probabilities. 1, collecting probabilities, PDF and all that. Yes. Third, extracting key info, which was moments. Yes. And then we came back to the second one to cover these examples of fx. Yes. So these were the first 3 modules, and everything was very nice over there. We were able to write everything nicely mathematically, define mean as summation x fx or integral x fx dx. Very nice formulations. We were able to say the probabilities of die rolling, showing 1, taking a ball randomly, or winning lottery for this case, all good. Yeah. But the 4th module is about something that is going to make things a bit harder. The reality is not that simple mostly. Yeah, that you are able to just look at the problem and assign probabilities. Okay, so rolling a die, winning lottery, many cases, yes, very good. But in most, or let's say in a large number of real problems related to probability, the assignment of probabilities, the decision on the PDF, and the extracting of the info, mean, variance, covariance, is not straightforward as we did for rolling a die and all that. The simple reason being that we do not have any logical or, let's say, meaningful formulation for that. Let me give you an example. Let's say we want to find the height. Yeah. So let's say we want to find the average height of people, adults in Slovenia. Yes. So let's go to that 4th module. I call it getting real. Okay. That is extracting key information from real data. Yeah. Now we often, and that is actually related to the second part of this more popular term, probability and statistics, right? What we did so far, very nice, all that was mostly probability, mathematical statistics or probability. Now we go to what we often call statistics, and that is where we have to go to collected data to extract information, mean, variance, and all those things. So let's see. Firstly, the word statistics, what do we use it for? कोई आपको याद इंग्लिश में या न्यूज़ में आप पढ़ते हैं, क्या क्या मीनिंग होता है इसका? Without going to any mathematics, यूज़ करते हैं ना लोग statistics. What's the meaning of that? So many people, you said two things now, data and information. Yes, so you covered both. More colloquially or in spoken English, often we use statistics to say the data we have collected. Yes, then we also use it to say the conclusion or the information we have driven from this data. For example, somebody may say, or you may read that I saw a statistic that most sea turtles live up to the age of 90. This is a statistic, right? Some info extracted. What's the info? That what is the lifespan of most turtles? You extract it. What's the average lifespan? What's the longest life a recorded turtle has lived? Yes. So statistic in our meaning or in our work will mean this thing. What is it? When you extract some information from collected data, we will call it a statistic. Okay, the tallest person in Swabi, that is a statistic. Okay, the average height of people in Swabi, that is a statistic. Yeah, so there can be lots of different statistics, and as you say, often we also use it to mean the data that's collected. In this course or for formal purposes, the data you collect is just data. We don't call it statistic. It's the information you extract from it that we will call statistic. They can be different. These, how much is the data spread out? That's another statistic. What's the average of the data? That's another. What's the mean of the data? Median, mode. What's the minimum of the data? What's the maximum value in this data? All these are information extracted from the data, and each one is a different statistic without the S. Okay, together they are statistics. Yeah. So now let's go into this and say, okay, I want you to find the average height of people, adults in Swabi. So कैसे निकालेंगे? क्या करेंगे? डेटा पता करेंगे, right? So would you डेटा कितना लेंगे?
Sample size with 20 करें.
Okay, so would you go to every person, every adult in Swabi and measure their height? Seems a bit hard to do, right? 1.5 million तो होंगे roughly adults Swabi में, yeah? So it doesn't seem very practical, does it? So yes, as you say, makes sense. You will sample. Yeah? So the population, from there you will sample. Second, can you write some precise biophysical formula to know heights of people? We don't have anything. We can have ranges, right? Height इतनी होती है, well shape हो सकता है. But there is no. We don't still have any formula to say कि अगर let's say we could find that in a particular population, what would be the exact height of every individual. नहीं बता सकते, कुछ है ही नहीं ऐसा. DNA भी दे दे तब भी डेटा तो आपको लेना पड़ेगा. So that means we are dealing with a random problem. There is uncertainty. We don't have very specific fixed models. Yeah. So if your answer to that, as you say, is what it is, then you are dealing with a problem of statistic. So what you would do, okay, you would have to let's say this is the population of Swabi adults, let's say 1.5 million, yeah. And let's say x1, x2, x3, x4, x5, x1000, x knots, maybe 10,000, x 50,000, whatever, and up to xn. This is the total population, adult population of Swabi. The height of any given person is a random variable. Yes, agreed? Great uncertainty. I can give you a range of people's heights, but I don't know what's the height of the 10th person you measure. Yes? So, each of these is a random variable. Yes? Now, from those random variables, you would collect samples, right? So, let's say you decide to measure heights of 1,000 people. Yeah. So let's say you do, and then you choose maybe, let's say, some 1,000 data points like this. This is sample 1 of size n1. Okay. Don't confuse. If there is x 50,000, it means there are all the people, but you chose only n1 of them. Maybe this is just 1,000 people. So in total, you chose 1,000 people and measured their height. What did you do? You sampled the population. Yes, from population you went to a sample. The problem is, what is the problem? The problem is the sample isn't unique. I could sample again 1,000 people, but a different 1,000 people, couldn't I? Yes. So another person may say, okay, I'm also going to sample maybe 1,000, maybe 15,000, but I'm going to take these and from here and some here. This one. Now this is sample 2 with some size and 2. Now even if the two sizes are the same, yes, even if they are same, the sample themselves are different. So if you say, okay, I will do like that, I will do sampling, that's fine, but then you have to answer 5 questions. Yeah, and what are those questions? Firstly, and the answer to those questions is this and the next lecture. Yeah, so what are the 5 questions you have to answer? कोई guess कर सकता है क्या क्या हो सकता है? I already gave some hint. Yes, you already mentioned one of them. So what are the questions you will have to answer if you are going for sampling?
Is the sample as big enough?
Size of the sample. Yes, that's one question. So what other questions can we ask? Average height. So average height is what we want to know. Yes, if you went to every single person in these 1.5 million, you will know the true height, true average height. You can find that, yes, for all 5 million, 1.5 million. We will call that the population mean. Okay, true height or true average. Yes, the population mean. But you are working with the sample. So one question that you would ask. This is the first question is, should the sample be random? What's your answer? What do you think? जो आप sampling करें, should it be random or not?
थोड़ी under control.
थोड़ी under control or कैसे?
सर अगर area different हो जाए लोगों का, suppose we would part that and train by.
So within Swabi, let's say you end up collecting heights of people from the same extended family. एक ही खानदान के 1,000 लोगों की आपने ले ली, extended family. Yeah. Is that a good way of finding the average height of people in Swabi? No, right? Because you expect some sort of correlation, dependence, right? एक खानदान है, DNA similar है culture. So why you should randomize? Yes. So yes, that is one question. Okay, random or not? Actually, you should go for random sampling. Second, how large should the sample be? Yes. Now, the answer to that, we will not answer all the questions now, but we will look at, it will depend a lot on what statistic you want to measure and what is the actual distribution of these guys. Okay, and how they are related. Are they all independent or are they correlated? So size is an important aspect here, size of sample. So what should be the size of the sample? That is one question, and we will look at it for specific or common cases later. Yeah. Third question, would different samples lead to the same statistic? So in this case, what is the statistic we are looking for? The average height. Yes. Now if you could measure height of all the 1.5 million adults in Swabi, very good. You got the exact answer, that's it. But that's not practical. You went for sampling. The problem with sampling now, the question you have to answer, should I go for random sampling? Yes, that is obvious. Like in size of the sample versus I have to give me a good enough estimate of the true one. Third one, as I asked, would different samples give the same answer, same average height or not? What do you think? So a person who sampled these 1,000 people, the white, and the person who sampled another set of 1,000 people in the red, even if the size is same, do you expect that the average you calculate based on that same होगा या different होगा? Different होगा, फिर तो बहुत सारे different हो जाएंगे, ऐसे ही है ना? So then what happens to your statistic? Now let's say the most common statistic actually for measuring the average is the x bar, is called the sample average, which we write as summation this guy xi is 1 to n. Yeah. Now I'm going to put here a 1 to tell me that this is based on the first sample. The average I calculate based on the first sample. Then the average I calculate based on the second sample would be how? It would be 1 over n2 summation. Now this thing, we, for our convenience, we are saying 1 to n, but it's actually whichever values you picked. Yeah, but for my convenience I will still say that. Don't assume that they are the same. Is 1 to n. Now these two will lead to different values. Yes. Now if they lead to different values, then a third person sample will lead to another value. So what just happened to your statistic, your estimate of the mean? The estimate of the mean. Now the mean is not a random variable. Okay. If you know the whole population, measure their heights, get their average, that's not a random variable. Yeah. But the mean you get from the samples is a random variable. Okay, so you are back to the problem of probability now. Yes, so the statistic you collect based on samples is itself a random variable. Okay, so what would you like now? That is the next question. So let's look at it. Then you would like to ask, okay, if x bar is itself a random variable, then क्या किया था हमने second module में? Distributions. Yes. How is x bar distributed? Is it normal? Is it exponential? Is it uniform? X bar हो गया ना, तय हो गया कि x bar itself is a random variable. As soon as you talk about a random variable, often the first question we ask is how is it distributed? What is its f of x? Yes. So that is the fourth question you will need to answer. So in this case, x bar is random itself. Yes. Then you need to ask, and it's not just x bar, it could be an estimate of the variance or some other statistic, the maximum height, minimum. So x bar is random. Fourth one, you want to know, okay, how is x bar distributed. What is the function here? What's your answer? More general answer is possible. Yes, it will really depend on the function of x bar, how the x bar is defined, and what are the distributions of each xi. Yeah. Fifth question that you will have to look at is, okay, is this a good estimate of the true mean? This is the true mean or the population mean. Yes, is this a good estimate, good or not? Yes, so is it a good estimate? And this is not just for the mean. I'm taking example of mean, but it's for any statistic that you draw from a sample. Okay, so now you should go for random sampling. Yes, what is the size of the sample? That is one question we have to answer. X bar is random, yes, agreed. But then what is the distribution of x bar? And then finally, what is a good estimate of x bar? Yeah? And answering these questions covers our fourth module, and a lot of this is basically part of inference theory, inferring from one information, yeah, inferring some key parameters or conclusions from data or from other information. So let's see. Let's look at. We've already answered the first question. To get started with these, we need to also define a few terminology here. We will call the true statistic, like the true mean, okay, as the population statistic. Okay, that means if you take a sample size equal to capital N, meaning you measure everybody, then the average you get, the variance you get, the minimum height you get, the maximum height you get is the true statistic or population statistic. So this is population mean. Yes, this is sample mean for particular sample. This is sample mean for another particular sample. Yes, so keep these in mind: sample statistics, sample mean, sample variance, population mean, population variance. Often what is happening, you are trying to get as close as possible to the population statistic using just a part of the population. That's the whole idea. Yes, एक sample आपने लिया है. Now whatever you conclude from that, you want कि आपका conclusion should be as, वरना फायदा नहीं है. आप every side में बता दें एक ही खानदान की ले और के स्वामी में लोग बहुत tall है, right? That will be wrong information. Yes, you want to get as close as possible to this, right? And we will see how to define when are you very close. What is a good estimate? Remember, you don't know the true value. ये भी बड़ा ट्रिक है. ऐसा नहीं अगर आपको ट्रू वैल्यू बता दूँ तो फिर कहूँ आपकी वैल्यू ये आई है तो कोई भी बता देगा माइनस करके कितना फर्क है. ऐसे ही है ना. But you don't know the true value, right? So you have to have some statistical guesses then. ये सारा, all of that comes under the concept of statistics, and within that inference theory. Right? There are graduate courses in full inference theory. In this course we will just see a very first trailer of inference theory: point estimation, interval estimation, hypothesis testing, yeah, and which again is also linked to classification theory. So from here on now, we will assume that whenever we are talking about sample statistic or whatever, sample mean or whatever, these guys are randomly chosen. Okay, that means we will assume they are independent of each other. Okay, and your book defines statistic as any function of a sample of independent random variables. Okay, so any random sample of independent random variables, but it's just not too specific there. So the only thing you need to be sure of is that this sample is selected randomly, so all xi's are independent of each other. एक खानदान के लोग नहीं हैं, ठीक है? So that is the idea. Now let's look at, so A, B, C is simple. We have already discussed that. Rest of the lecture is on D, which is, what was question D? Or question 4 here. How is X bar distributed? Yeah. So okay, let's look at how they are distributed. Firstly, we will talk about in this course mostly about two statistics that we collect from here. Okay. This kind of thing. One statistic that we often work with is the estimator of the true mean. This is the true mean that you want to get to. The estimator of that based on sample, called sample mean, is often, or this is the most common one used, is this guy. You take n samples, you average them. That's your best guess of the true mean. So true mean or population mean, sample. What about variance? Sigma squared. We have a symbol for that, we call it S, and that is calculated based on sample like this. 1 over n minus 1 summation xi minus x bar square. Now compare these to the theoretical ones. Theory में क्या था mean? What was it in theory? Let's write it here. Mu was E of x. For discrete case, it was summation xi f xi. ऐसे ही था? Yes. But now you are getting real. This is the fourth module. This is no longer good. You want to work with samples now. So this is your average. Similarly, variance क्या थी? What was the formula for variance? P of x. याद है किसी को for discrete case? Yeah. Okay. xi minus mu square times fxi. Now this thing is now replaced by xi minus the estimate of the mean, the sample mean. So this is called sample mean, sample variance. Now when you estimate, different people, different mathematicians, they can put their own estimator in forward. How do you decide which is good? There are trade-offs. We will see that later. For example, somebody might say, okay, I don't want to divide by n minus 1, I want to divide by n. Is that better than this? How do we know? So we have to define some measures, some indices. What is a good estimator? Yeah, we will see that later. But today, we just try to start the thing. Now, these are not the only two things you can extract from here. There are lots of statistics that you can extract from the data. But for a first course, this is the most common. Then sometimes we can discuss the ratio of the means of two different samples. That's a different statistic. It gets a bit more advanced, but if you understand what we're developing now, the idea remains the same. Okay, so let's look at that mean and the variance. What was the question we were looking at? We were looking at how are they distributed. Okay, because we now know, okay, my estimate x bar, the sample mean, is itself a random variable. My estimate s, the sample estimate of variance, is itself a random variable. Then I want to find out, okay, How are they distributed? Why do I want to find that out? Because I want to know if they are good estimates or not. So we will see that. Let's take this away and stick to what we have here now. So we will look at several cases. First, let's talk about the sample mean. Okay, this guy. So the question we are asking is, how is X bar distributed? It has some distribution because we know it's random. And what is this distribution? I want to find that out. Okay, so we will look at two cases. First case, if the xi is calculated from xi, yes, this random sample. If xi are all normally distributed with same mean and variance, if that happens, then what do you think is the distribution of X bar? Any guesses? D. Now it will still be Gaussian distributed because you are just summing up Gaussian variables, okay, and dividing by n. So the first case is if the underlying data samples are Gaussian. Remember, we are already assuming in all these that they are independent, that they were coming from a random sample. So that is already assumed. Additional assumption is that they are all Gaussian distributed or normally distributed with the same mean and variance. Then it can be shown that X bar is actually normally distributed with mean and with mean mu x bar and variance sigma square x bar, where the mean mu x bar is actually the same as the true mean, and sigma x bar square is the true variance divided by n. Okay. So if the underlying data is Gaussian distributed with same mean and variance, then the sample mean is also Gaussian distributed. Okay, its mean is the same as the true mean, its variance is a bit different, sigma square by n. Okay, and you can show that. For example, how can we show the first one? Can somebody help me? That the mean is mu. The mean of x bar is the true mean. How do we prove that? Very simple. Yes. क्या होगा? Now apply E operator to both sides. Yes. So E of x bar equals 1 over n. The other we said the expectation is linear. E of x plus y is ex plus ey. So these are all summations. So it will be summation I is 1 to n E of xi, isn't it? But what is the expected value? What is the mean of each one of them? You already said each one has the same mean, mu. Yes. So how many mu's here? 1 over n times mu plus mu up to n mu's. So this is n. Yes. So mu x bar, the mean of x bar is the true mean. So this guy is a good estimator, yeah? Especially if n is a if xi are Gaussian distributed. Now what happens if xi are not Gaussian distributed? Okay, then the central limit theorem tells us, if you remember, the central limit theorem that whatever the distributions of the underlying random variable, their cumulative effect slowly or sometimes very fast converges towards Gaussian distribution. So case B is, let's write that, this was case A. Case B is that xi not Gaussian. Okay. Then there are several further cases, but in this case we will assume that whatever distribution they are, maybe they are coming from uniform distribution, exponential distribution. Okay, what we will assume only is that whatever distribution they are coming from, they all have the same distribution. So all of them are either Gaussian or the exponential, all uniform, whatever it is, but not normal. If it is normal, we already covered the case. Yeah. So now for that case, in fact, since we assume they have the same whatever that is, so the distribution of the sample mean will approach as n increases, the size of the sample increases, the distribution will approach the true mean, Gaussian distribution with true mean and sigma square over n. So here the distribution is actually Gaussian with mean mu and variance sigma square over n. In this case, as long as the sample size is large enough, the sample mean will have a distribution which is Gaussian. Its mean is the true mean, its variance is the true variance divided by n. Okay, so now a rule of thumb पता क्या होता है? You know, yeah, something based on practice or practical knowledge. Rule of thumb is that if n is, maybe there is equal also, or just, yeah, if n is greater or equal to 30, so if your sample size is greater or equal to 30, you can easily assume that your sample mean has normal distribution. Okay, this is a result of central limit theorem. So for the sample size n greater than or equal to 30, you are in safe hands. Okay, for the size smaller than that, okay, then it will really depend on what these distributions are. Are they uniform? Are they exponential? There are so many others. Yeah. So what about if they are all Gaussian? Then this rule does not need to be covered. Okay. If the random variables xi themselves are all Gaussian, you don't have to collect 30 of them to have a Gaussian distributed sample mean. Then it is always Gaussian. Okay. This rule only comes in if you tell me that the original sample guys, this guys, the things that I am measuring are not Gaussian. Okay. Only then this rule comes in. For that, it's always there. So these are the two cases that we cover. Let's see if we use the time. Still have some. I will cover some more and then we will stop. We'll leave the last question to next lecture. So what about the statistics of the sample variance? Any questions on this? कुछ याद है हम हैं कहाँ पर? A lot going on, I know. Remember this. Let me just recap, maybe that will help. We said that we wanted to find the average height of adults in Swabi. Yes. Now, if you could measure the actual height of every single adult in Swabi, 1.5 million people roughly, you would be getting the true average, which would be we'll call it mu, or the population average. We said, well, that's not practical. Let's do what? Let's take a random sample, yes, of size n. N can be 1000, 2000, whatever. Let's take a random sample of size n, observe their heights, and then just average them. एवरेज ऐसे ही होता है ना, आपको 10 नंबर दो तो क्या करते हैं, 10 को ऐड करते हैं, डिवाइड बाय 10 कर देते हैं, ऐसे ही है. So this is what you did. You said I will observe n of them and I will average their heights. This will be my guess, my estimate of the average height of adults in Swami. So this we said was going to be x bar. Yes, and this we said is a statistic. It's based on a random, if you base it on a random sample, based on it's a function of a random sample of random variables. Okay, that is the idea. The sample itself is random, and then every one of the variables itself random. So it's a function of the random sample of random variables, because you had the heights of people, right? Each one was a random variable. Within the चौथे बंदे की height क्या होगी? Okay, so it was a random sample of random variables, and then you did a function on that. What was the function? You sum them and divide by them, and that is called a statistic. And they can be, as you can imagine, as many functions you can make, as many statistics are possible, but not all are meaningful. Yeah, so this is a very meaningful statistic. What is the average height? Yeah, so then we said, hang on, since this guy, one person could have one sample, another could have another sample, even if n is same, they could have different samples. So they would give me different answers. Yes, so they will say, if this is x bar, one will say the mean is this, another will say the mean is this, another will say what the mean is this. It's a random variable. So then we realize, hang on, this is a random variable. Then I want to know, okay, if it is a random variable, what is the shape of distribution? Is the shape of this random variable distribution uniform? Yeah. Is it exponential, or is it Gaussian? That was the question we were asking ourselves. And we found two cases. We said, if each of these is Gaussian with same mean and variance, then this guy is definitely Gaussian. Yes, with the mean mu and if these guys are not Gaussian but come from some other distribution, but all of them coming from the same distribution, then as long as n is greater than 30, you can be sure that this guy will be Gaussian approximately, and the approximation keeps getting better as you go higher. But from 30 onwards, you can easily assume that it is very close to thoda bahut hoga. And if you get even higher, then it will become exactly Gaussian. Yeah, that is the distribution of this guy. Now, the second most important statistic we cover is the spread of the data, variance. Yes. So we said, okay, now I'm not interested just in the mean average height of adults in Swabi. I also want you to tell me what is the spread, the variance of the heights of adults in Swabi. Again, you go to 1.5 million people, you measure their heights, you calculate the variance, that is the true value. Fine, but not practical. So you say, okay, just like this guy, I will do this. I will take a random sample. So I will take a random sample and I will use a formula like this one, summation xi minus x bar square, and this I will call my estimate of the variance. Now this is a statistic. Why is it also a statistic? Look, it is a function of a random sample of random variables. So it is a statistic. And this statistic represents the variance, which is sigma square, the true value. Just like x bar, we realize that S is also a random variable because samples will vary. Yes, so if S is a random variable, then S should have some distribution. Now, what is the distribution of S? This is our next question. We have already answered this question for X bar. Remember, in general, you cannot give a general answer that the distribution of X bar is Gaussian. You have to make assumptions. Yes, if the underlying variables are all Gaussian, yes. Are they more than 30? Yes, no. Depending on that, the answer will change. So I gave you two very common cases. Same here. I can't give you a general answer. Yeah, because it will really depend on these guys. But let's look at the case. I will not prove it here, but it can be shown that the random variable defined as n minus 1 s square, sorry, this is s square formula, over sigma square. You recognize this is the sample variance. This is the true variance. That is, if you had chosen small n equal to capital N, then you should get this. Yeah. So this is your sample size minus 1. Okay. It can be shown that this variable, which we will from here on call chi square, the Latin character or Greek character chi, the or chi भी पढ़ते हैं, chi square. Yeah. So we're used to saying chi, so I will stick to chi. Chi, we call it chi square. It can be shown that this random variable has a distribution that we call the chi squared or chi square distribution. Now I haven't covered the chi square distribution in this course, right? But it's a continuous distribution. What did we cover? Continuous uniform, exponential, and Gaussian. But the chi square distribution, as long as you know what a distribution means, each distribution can have a different function, that is enough. But what is important here is to see this. And what is the shape of the chi? I won't write the formula because it involves gamma functions and all that, and I don't want you to get confused. It's just some distribution. Yeah. Now, why this shape? Why not the distribution of s square alone? It's very hard to find the distribution s square alone, but this form is very useful, as we will see in the next lecture. When we say is s square a good estimator of sigma square, then we will see that this formulation is very useful. Okay. So now the chi square distribution has some properties. What are its properties? Firstly, it is asymmetric. Symmetric का पता है? Gaussian is symmetric. Yes, एक किसी भी point आप middle point के लिए वो same होती है, mirror image होती है. Chi square distribution is asymmetric. It is continuous distribution. It has a parameter. What was the parameters of Gaussian distribution? दो parameter, mean and variance, sigma and square and mu. इसके फॉर्मूले में आ रहे थे ना वो 1 over square root 2 pi sigma all that. Now the chi square distribution has parameter called nu, whose name is degree of freedom. ये लफ्ज़ सुना है आपने कभी? Degree of freedom. नाम से ऐसा लगता है डिग्री जो आपको आज़ादी देते हैं. या बट रोबोटिक्स वगैरह में जो लोग इंटरेस्टेड है, अगर इफ़ योर रोबोट कैन मूव टू मेक अ रोबोटिक आर्म, इट कैन ओनली डू दिस एंड दिस इज 1 degree of freedom. Yeah, if it can do this and this is 2 degree of freedom. And if it can also rotate 3 degree, तो वो रोबोटिक्स में भी इसका कॉन्सेप्ट. बट हियर also it has something to do with um, the number of independent parameters. लेकिन वो थोड़ा सा complicated है, I won't go into that. Yeah, just know that this guy, a special function of this n minus 1 s square sigma square, let's call it chi square. It's not equal, we're just giving it a name, denoting it like that. Yeah. So chi square has a chi square distribution. The chi square is symmetric, it's continuous, and it has a degree of freedom parameter mu, which is equal to n minus 1. So what does that mean? That means that this distribution shape will change based on your sample size. And is sample size, right? So if you change the sample size, mu will change. If mu changes, it's a parameter of the distribution. Gaussian में क्या था? mu change होता था तो वो इधर चली जाती थी, इधर चली, right? Sigma change होता है तो वो spread out हो जाती है, thin हो जाती है. इसके लिए you have to change mu. Its commonly drawn shape is this guy. Yeah. ये almost like you clip the Gaussian on the left side. So ये यहाँ पे it's actually exactly 0. It starts at 0 and then goes up, and here it asymptotically approaches the x-axis. Okay, so it's asymmetric. Gaussian तो full. If you were drawing a Gaussian here with this mean, it would be like this. Yeah, दोनों तरफ चलती रहेगी वो. Yeah, this guy has a kind of a lump towards the right, and that lump changes with sample size. Okay, so but in effect this is asymmetric, continuous, has a parameter nu, so it doesn't really show here exactly. वो थोड़ा complicated है, but that's the case. The last one I will mention before closing the lecture is in estimating the mean and variance. We often need to look at another case. So let's quickly do that. We often need to look at this situation also, where you have the x bar minus mu s over square root of n. Okay, so this is a situation, we'll come back to this later, but this is a situation where you have now two estimates or two random variables. क्या क्या है? X bar and s, the sample mean and the sample values. If they show up together, then this particular form, which we will next lecture see, it has very great uses for us, also has a name. We call it T. Okay, chi किसको कहा था हमने? Chi was n minus 1 s square over true sigma square. There is only one random variable here, this time. Yes, and we named it chi square, and we said this whole new random variable, which has a name chi square, has a distribution which is the chi square distribution, asymmetric. On the left it's 0, then it rises, then it falls and keeps going asymptotically. That was the chi square distribution. This guy has a t distribution, which again we will not cover this course. It also has gamma functions, बड़ी वो लिखते हैं थोड़ी सी complicated लगती है, and then gamma functions are not easy to calculate. उनके table होते हैं या you use computers for that, but I focus on the idea that this guy has a distribution. T has T distribution. Actually इसीलिए ये नाम भी T ही दिया गया इसको, ये वाला T distribution. And now what does the T distribution look like? Well, what did we say about chi square? Was it symmetric or not? So chi square was asymmetric, yes? Gaussian is symmetric. Now for the case of T distribution, it is actually symmetric, continuous. It also has a bell shaped curve. Okay, so it is symmetric, it is continuous, it is also bell shaped, but with heavier tails. I will explain what we mean by heavier tail. And it also has a parameter called nu, which is again called the degree of freedom, and that for this particular case nu is n minus 1. So the shape of this distribution again also changes based on your sample size. Okay, nu equals n minus 1, and if nu equals infinity, then this distribution approaches Gaussian or normal distribution. What do we mean by nu equals infinity or approaches infinity? That means sample size is very large. If the sample size is very large, you are back to normal distribution. Now, how does the t distribution look? Well, I need space here, so we draw that and then we end the lecture. The t distribution looks like, as we say, it is symmetric, it is a bell curve. Yes, so how is it different from Gaussian? First I will draw Gaussian. Yeah, let's say this is our friend, the Gaussian curve. Now we already said this is for nu equals infinity, and the sample size is very large, the t distribution becomes Gaussian distribution, and this is your Gaussian distribution. But what about when it is not very large, the sample size is not infinite? Well, then now what happened here? I didn't draw it symmetrically, mushkil hai, but imagine he is symmetric here. Okay, it remains symmetric, but notice what happened. These are called the tails of the bell curve. Yeah, decided it. Look, the tails got heavier, they're thicker. More probability is leaking towards the tail. Gaussian में क्या होता है? Tails have very low probability, zero की तरफ asymptotically, exponentially जा रही होती है. This guy slightly more probability here, so they are thicker, and this might be nu equals 5, for example. What about, let's draw another one, which would be, let's say, nu equal to. If I reduce the sample size further, what do you expect will happen? The tail will get even more thick. Okay, so it will be, this is for nu equals 2. Very small. आपने सिर्फ 3 सैंपल n-1 है ना, ये तो सिर्फ 3 डेटा 3 लोगों की हाइट में रखी है. Yeah, so in that case this goes away from Gaussian. So this is the t distribution. I'm not writing its formula, आपकी बुक में है, आप पढ़ लें just to get an idea, but it's a lot of gamma function. आपने पढ़ेंगे gamma function. Okay, basic math, right? They are a special class of functions. जैसे आपका cosine sine होते हैं ना, इस तरह ये भी एक पूरी class है functions की. Not very friendly functions. Okay, usually you don't have to deal with them. You can cosine sine का आप क्या करते हैं? कैलकुलेटर में डालते हैं. gamma का भी करना होता है, right? I know I shouldn't be saying that कि कोई function इतना अहम नहीं है, पर for most engineers gamma functions are just functions की value डालें और निकालें. Here what I want you to understand is that that the sample size will affect how your this guy was x bar minus mu divided by s over square root n. These are both random variables. What is the distribution of this statistic? This whole statistic, which is based on 2 other random statistics. Yeah, we said if we call it t, then it's called a t distribution. In literature, we also write it as students t distribution. There are 2 names for t distribution. This is t distribution. Its shape changes based on nu. If nu is infinity, it becomes exactly the same as Gaussian. So Gaussian is a special case of T distribution. Okay. Now the other name, students T distribution, is the full name of it. Why students? There is a very interesting history. I tell you that, and then we end the lecture. The guy who came up with this distribution for the first time, he was working at a company that did not allow publishing their work. Okay, so what he did was he published a paper, and the author name he sent was student. Okay, so since then it's being called, because that was the first person, it was in 1940s or something. So books usually call it students. That guy whose name is that, now we know his real name, but at least when it was published, he was known as student. Okay, so thank you so much, and next time we will answer our last question, which was, what is a good estimate? How do you know? Yes, अभी तक हमने कुछ उस पे बात नहीं की. So we will know that, discuss that, and we see where we wanna go. Any questions? No? Okay. Thank you so much.